Initial training on next token prediction yields vast knowledge, but provides zero ability to follow specific user instructions. To transform that raw predictive text engine into a helpful, aligned assistant, we execute a mandatory second phase of training called alignment. For years, the gold standard for this phase was reinforcement learning from human feedback, or RLHF. While RLHF successfully created modern chatbots, it introduced a hardware barrier that effectively locked smaller research teams out of reinforcement learning optimization. At the hardware layer, running a single large language model requires massive GPU memory, commonly known as VRAM. This diagram shows the first component of RLHF, the policy model. This is the actual language model actively being updated during training. But RLHF also requires a reference model. This is a frozen copy of the original model, kept in memory to prevent the policy model from degrading into gibberish. Then it requires a reward model, a separate neural network trained to score outputs based on human preferences. Finally, relying on proximal policy optimization, it needs a value model to estimate advantage during generation. To run this single optimization loop, 4 massive neural networks must be loaded into memory simultaneously. For a 70 billion parameter model, that means allocating hundreds of gigabytes of VRAM before a single parameter can be updated. This massive hardware footprint frequently results in fatal out-of-memory failures during the active optimization training phase. Even when the hardware is capable, RLHF is notoriously sensitive to hyperparameter tuning, making the process highly unstable and difficult to reproduce. This brute force approach restricted advanced alignment to companies with massive GPU clusters, forcing the rest of the industry to search for a mathematical bypass. The first major algorithmic workaround to this VRAM bottleneck arrived in the form of direct preference optimization, or DPO. DPO circumvents reinforcement learning entirely. Instead, it utilizes static, offline preference data, specifically datasets containing pairs of chosen and rejected responses. The core mathematical breakthrough of DPO was reparametrizing the Bradley-Terry preference model. This diagram shows a variable transformation, where researchers proved that the reward model is implicitly defined by the log ratio of the policy model and the reference model. This substitution completely eliminates the need to load an explicit reward model into memory. The reward is calculated directly from the networks you already have. Furthermore, DPO drops the value model as well. Now only 2 models remain in VRAM. The DPO loss function simply operates by increasing the probability of the chosen response in the dataset and decreasing the probability of the rejected one. DPO democratized alignment. Trading a bloated model architecture for an elegant mathematical loss function, developers saved massive compute costs. However, DPO contains a strict limitation. It is an offline algorithm, tethered entirely to static datasets. Complex reasoning, coding, and mathematical problem-solving cannot be effectively taught using only pre-written human examples. There are simply too many viable logical pathways. Developing multi-step logic requires live online exploration, where a model must try different logic paths and learn from its mistakes. To build models that verify their own logic, engineers had to return to online reinforcement learning, which risked reintroducing the value model. When DeepSeek set out to build a frontier reasoning model, they refused to rely on brute force GPU clusters. Their engineering requirement was clear. They needed live online exploration, but they could not afford the massive VRAM footprint of a value model. A value model establishes an absolute baseline score. It tells the system if a generated action is better or worse than expected. The mathematical challenge became, how do you calculate the advantage of a specific model response if you have no value network to provide that baseline? Their architectural answer to this missing baseline is Group Relative Policy Optimization, or GRPO. GRPO solves the baseline problem without introducing a new neural network. Instead, it leverages statistical sampling during generation. The primary mechanism of GRPO is generation volume. Instead of generating a single answer for a prompt, the model generates a group of varying outputs. Each output in this group is immediately evaluated and assigned a rule-based reward score, for instance, checking if a final mathematical string is correct. First, we calculate the average score of that specific group, denoted as mu. Second, we calculate the standard deviation, defining the spread of those scores. This yields the full GRPO advantage equation, dictating how the model updates based on relative advantage. In the numerator, the equation subtracts the group's average score from the individual output score, proving whether a specific output performed better than its peers. In the denominator, it divides by the standard deviation. This normalizes the advantage, preventing extreme updates and keeping training stable. This relative advantage calculation perfectly replaces the absolute baseline previously provided by the value model. The efficiency gain is massive. GRPO achieves active online exploration while only requiring the policy and reference models to be loaded in VRAM. By forcing responses to compete against their own group average, GRPO achieved state-of-the-art reasoning without the memory footprint of a 4-model PPO stack. At the deployment layer, open-source engineers must now choose between these two optimized architectures based on their specific goals. The ideal use case for DPO is standard instruction tuning, like general chatting or summarization, where you already possess a high-quality, fixed dataset of human preferences. However, a well-documented bias of DPO is that it tends to produce overly long responses, requiring careful monitoring during deployment. GRPO, on the other hand, is built for scenarios requiring multi-step logic, where the final answer can be programmatically verified on the fly. Specific targets for GRPO deployment include competitive programming, complex mathematics, and autonomous agent workflows. Ultimately, the choice between DPO and GPRPO is determined entirely by whether your reward criteria are static or verifiable in real time. In just a few years, the industry evolved from the brute force 4-model architecture of RLHF to the mathematically optimized 2-model architectures of DPO and GPRPO. This image of server racks illustrates our new reality. Algorithmic efficiency is now doing the heavy lifting previously assigned to physical hardware. The next frontier of artificial intelligence belongs to those who optimize the objective function as aggressively as the hardware it runs on.